So I'm about to start with exterior calculus, but let me just finish up with estimates for in the abstract setting. So we proved these improved error estimates, and we got more and more terms coming in as we moved from d sigma to sigma du and then u. And so this u1 is the most complicated one, but it's also good enough for the applications. Now I want to turn to the eigenvalue problem just quickly and make some comments. So whenever you have a PDE LU equals F, you can also ask about the eigenvalue problem, LU equals lambda U, and try to compute the eigenvalues and the eigenfunctions. So the eigenvalue problem for the abstract Hodge-Laplacian is we're trying to find an eigenvalue lambda and a non-zero eigenvector u in the domain of L such that LU is lambda u. And actually here I could either put in u as orthogonal harmonic or not. If I leave it out, then I'm saying then the harmonic things will pop up as the zero eigenvalues. Or if I take it out, I'm saying find the non-zero eigenvalues of L. It's a little easier notation-wise to take it out. In this problem, if we get rid of the harmonic functions, so we are only talking about non-zero eigenvalues, they're all positive. That's basically saying L is a positive definite operator. And the proof is very simple. Just take the equation LU equals lambda u and multiply by u. Take the inner product with u, so you get lambda u squared is du squared plus d star u squared. We can, if we wish, then for the non-zero eigenvalues, since I got rid of them, we can invert L and invert lambda and write it as ku equals lambda inverse u. So the eigenvalues for L are the same as the eigenvalues for k, except they're the inverses. And since we assume that k is a compact operator from W to W, the eigenvalues of a self-adjoint compact operator are a sequence approaching 0. And so their inverses are a sequence approaching infinity. So the eigenvalues of the abstract Hodge-Laplacian, as long as we have the compactness property, are a sequence of positive numbers, possibly with repeats, of course, multiple eigenvalues, going off to infinity. And we'd like to compute some of these and get some approximations to those and to the eigenspaces. Give a name to the eigenvector, so let vi be the eigenvector corresponding to lambda I. Normalize it so it's of length 1. And if there are no multiple eigenvectors, they're automatically orthogonal to each other. Eigenvectors for different eigenvalues of a self-adjoint operator are orthogonal. If you have a multiple eigenvalue, say lambda 1 equals lambda 2, well then really v1 and v2 are not determined. Just the span of the two of them is determined, and you could take any orthonormal space for them. That makes it a little bit difficult to talk about convergence, because you can't say my v1h converges to v1, because you have to specify how did you pick v1. You could have picked anything in the space. So people who work on eigenvalue analysis have long had to deal with that headache. But so take any orthonormal basis of eigenvectors, which you have some freedom on, especially if there's multiple eigenvectors. Let vi be the eigenvector and ei be the span of that eigenvector. The numerical method is just take the mixed method we had before, but instead of fv here, put lambda hu hv, where lambda h is a discrete eigenvector to be determined. And of course, this comes down to a big matrix eigenvalue problem, and you put it into SLEPC or some well-known matrix, sparse matrix eigenvalue solver, and you can solve the problem. And then the question is, do the lambda h, so now this is finite dimensional, so you only have finitely many lambda for this thing, lambda 1h through lambda n sub hh, and as the mesh is refined, you get more and more of them. And do these things, are these close to the correct eigenvalues? And then this has an orthonormal basis, and are these close to the correct eigenvectors there, taking into account this, this fact that they're not quite unique. You have to normalize in some way. Okay, and the way to study such problems is pretty well understood now. We're in the nice case, if we think of it in this primal way, the nice case of a self-adjoint compact operator. So this is how you define convergence. You have to be careful when you define convergence. The first definition you might write down would say, okay, so you maybe compute 100 eigenvalues, because that's the size of your matrix, and then you compute with a finer mesh and a finer mesh, and then what you want is to sort of follow one eigenvalue and make sure it converges to an eigenvalue of the true problem. And that way you might get the first 50 eigenvalues of the true problem, and then if you refine your mesh and have even more, you might get very close to the first 100 eigenvalues of the true problem and so forth. But you have to be careful, even if you write a definition that says each of the eigenvalues of the true problem is the limit of eigenvalues of the discrete problem, maybe you'll have some spurious extra things, some extra limits. You don't want that. So people have worked out a nice definition for eigenvalue convergence that avoids that, and here's the definition. You take the sum of the span of the eigenspaces, not of the first j eigenvalues, but of the first j distinct eigenvalues. So if there's some of these may be multiple eigenvalues. So this is a space of dimension mj, which could be bigger than j. So if you have a multiple eigenvalue, you throw in all the eigenvectors, and that way this quantity doesn't depend on how you chose your basis for the eigenspace. This is the span of all the eigenspaces of the first j distinct eigenvalues. It's a meaningful quantity. And you say that the method converges if for any epsilon greater, any j, any number of eigenvalues, and any epsilon greater than 0, if the mesh is sufficiently fine, essentially, if h is sufficiently small, then the maximum difference between the ith eigenvalue and the ith discrete eigenvalue for I up to this number mj is less than epsilon. And to get eigenvector convergence, the span of the first j distinct eigenvalues, that mj dimensional space has a gap with the discrete version of it, which goes to 0 also. So that would say that the eigenvalues converge and the eigenvectors converge, and there's no spurious stuff going on. It doesn't say anything about the rate of convergence. This is just convergence. For all epsilon greater than 0, there exists an h. There's a very simple, necessary, and sufficient condition for eigenvalue convergence that comes out of the theory of eigenvalues of compact self-adjoint operators and the perturbations, which is, say, in Cato's book. And there's a big handbook article on finite elements for eigenvalues by Babushka Osborne. There's a lot of very nice recent work by Bofi, Bretzi, and Gastaldi, that group. And here's the necessary and sufficient condition. I think these three guys proved it was necessary. For a long time, it's been known to be sufficient. And it's done using spectral integration theory in the complex plane and resolvents and stuff. So here it is. Look at, so we have the solution operator K, which goes from W to the domain of L, which is contained in W. So let's just think of it as an operator from W to W, and it's compact. Then on the discrete level, we have a KH. And this goes from WH to WH. And the discrete solution UH is KH of what? Well, you have a term that looks like FV for all V in the subspace. So this is, F is only seeing the subspace, so it's KH applied to the projection of F into VH. This KH operator is only defined on the finite dimensional space. So here U is equal to KF, and UH is KHFH. Okay, so we have these two operators. Let's see, right. And so this operator here, KHPH, of course, goes from all of W, puts it into WH, then solves the finite element system, and gets you to WH, which is part of W. So they're both linear operators from W to W, and therefore you can compare them and take the norm. And the condition is their difference as a linear operator from W to W converges to 0 in operator norm, not pointwise. If that happens, then that implies this. which is eigenvalue convergence in the strongest sense, or in a very strong sense. So that reduces the question to, can we prove from our error estimates? This is the solution operator. So this is really a question about the source problem. If you have the true solution of the source problem minus the finite element solution of the source problem, does that go to 0 in this operator sense? Okay, so now you write down the error estimate we have for u minus UH. That's k of f minus kh of PHF. And this was the error estimate we had from the improved error estimators. It had all those terms. And now the brackets match up. And we just look at them one-to-one. So what do we do with EU? That's the best approximation of U. Well, delta measured the best approximation of something of order 1, the best approximation of KF. U is KF. So this is just delta times F. And delta is a quantity going to 0, so this term goes to 0. E of du, for the very similar reasons, the quantity was known as eta for the best approximation of d of kf. So we get eta times f for this term, and eta times f for the sigma term, because that's d star u. So these two terms actually have an eta squared in front of them, so they're definitely going to 0. Now these two stars have an eta squared and a delta in front of them, and we're already going to live with an eta squared and a delta, so we don't even have to worry about these terms. We can bound these by 1. And we can certainly do that because E of d sigma is certainly less than, it's the best approximation, so it's not better than d sigma itself, which would be the 0 approximation. So these ones are all just bounded by f, because d sigma is bounded by f from the well-posedness of the problem. So you plug all that in, and you get that k minus kh phf, that's u minus uh, is bounded by delta times eta plus u, all of this times the norm of f. This times the norm of f, and therefore we have norm convergence. The norm is bounded by delta plus eta squared plus mu, which goes to 0 by compactness. So the conclusion of all that is that eigenvalue convergence just follows from the improved estimate and known spectral theory. Then, of course, as numerical analysts, we don't really care about convergence. We care about convergence with some decent rate. Then you go back to papers like Babushka and Osborne or Bofi, Bretzi, Gastaldi, and the arguments have been well worked out how you get rates of convergence. And the typical thing you see is that the eigenvectors converge about as the same rate as the source problem in the energy norm, and the eigenvalues converge at about the square of that rate. That's typical. And that can be proved in this case also. And so you get eigenvalue convergence like h to the 2r typically. Okay, that's all I'm going to say about eigenvalues, unless there's any. And now I want to get to a major new chapter. So back on the first day, we had this slide where I said, what's this de Rham complex? What does it mean? When I was first introducing it, and I said, well, in 1D, just take functions, differentiate them, and get functions again. In 2D, that becomes gradient to get vector fields and rows, and 3D, grad curl div. And I said we could do it on smooth functions, and then we get a complex called the de Rham complex. Later, we decided we really wanted Hilbert spaces, so we introduced, H1 and H curl and H div and so forth. And I said this can be done actually on any domain in Rn, or even on any manifold. And what's more, when you do it, you get a nice uniform definition for D, and the things you get out have the property that the K forms are integrable over K-dimensional simplices, and you get a Stokes theorem and so forth. So now I want to actually do that. So this is way back from Henri Cartan, the exterior calculus. So exterior calculus starts with some ideas that are merely algebraic. So it's linear algebra, finite dimensional linear algebra, and then you add some calculus, different derivatives and integrals on top of it. So let me start with the algebraic part. So I'm going to start really simple. If we have a vector space, all it is a finite dimensional vector space. Then we already know one part of exterior algebra. We know the dual space. This is a space of linear forms from V to R. So we can also talk about bilinear forms from V to R. So this is just linear forms V to R. We could also talk about bilinear forms from V to R, or trilinear forms from V cross V to R, and so forth. And so I will call this, in general, lin K. Will be K-linear forms from K copies of V to R. So there it is. They're linear in each of the K arguments. So lin1 of V is just the dual space, the space of what's called either covectors, dual vectors, or in this language, people call them one forms. So you can call the bilinear ones two forms and so forth. And you should also have zero forms. A K form takes K vectors and gives you a number. So a zero form takes nothing at all and gives you a real number, so it's just the real numbers. Now we're going to define a bunch of products of these kinds of objects. The tensor product is the easiest one here. If you have a J form and a K form, the tensor product is the J plus K form, where you stick the first J arguments in the first guy, the last K arguments in the last guy, and you multiply them together. The dimension is n to the k, and how do we see that? Well, first of all, let's look at one forms. We determine a one form by what it does on a basis vector on V. If we know its action on each of the basis vectors, we know its action on everything. So the dimension of the dual space is the same as the dimension of the space. So lin1 has dimension n, where n is the dimension of V. A two form, a bilinear form, we'd have to say what it does on, say, any two basis vectors, say EI and EJ. If I know this, then I know what it does on everything. And I can specify these numbers arbitrarily, so I get n squared and so forth. Now, on an arbitrary vector space, I can choose any basis I want here. Rn differs from an arbitrary n-dimensional vector space in that it has a preferred basis. So when I say Rn, I mean actually n tuples of numbers, and so there are these special basis elements E1 through En, right? So when the color coding here is when I go into this brownish color, I'm saying something specific for Rn rather than just any n-dimensional vector space. There is a preferred basis, Ej, and so there's a preferred dual basis, which we use the somewhat odd notation, dxi, with the meaning that dxi applied to Ej is delta ij. And then the basis for K-linear forms is you just tensor product any choice of dx sigma 1 through dx sigma k. This would be the guy that takes E sigma 1, E sigma 2 through E sigma k to 1 and takes anything else like E1, E3, E5 to 0, unless that 1, 3, 5 is this choice here. So that's a basis for this n to the k dimensional space. Okay, not much there. Now we add one more ingredient. We ask the multilinear forms to be alternating, at which point we would call them algebraic K-forms, as opposed to what we'll study in a moment, differential K-forms. The relationship between algebraic K-forms and differential K-forms is the same as between vectors and vector fields, or matrices and matrix fields. So this is just the vector sort of object. Alternating K-linear form. Alternating means if you switch two of the guys, you get the negative. In particular, if two are the same, it must be 0. So one of these ones is determined by less information. If you stick in k vectors, k basis vectors, you can always keep flipping them around till they're in increasing order. And if you know the effect on an increasing sequence, E sigma 1 through sigma k, where the sigma 1 through sigma k is an increasing sequence, then you know everything. So it's the number of increasing sequences of k things chosen out of n, so it's n choose k, is the dimension of alt k. There's a nice operator that takes any k-linear form to an alternating k-linear form, which is you take its skew symmetric part, which means you apply it not only to v1 through vk, but also all permutations of v1 through vk, and you add them all up with alternating signs depending on the permutation, take the average, that's called the skew part. So for example, the skew part of a bilinear form applied to v1, v2 is 1/2 of BV1V2 minus BV2V1, right? And the skew part of a trilinear form applied to V1, V2, V3, well, you'd have to take all 6 permutations. So you'd have BV1, V2, V3, and then V2, V3, V1, and V3, V1, V2, and then you'd have the other 3 combinations where BV2, V1, V3 with a minus sign, BV3, V2, V1 with a minus sign, BV1, V3, V2 with a minus sign, and you take a 1/6 of that to make it sort of an average. Okay, then that allows us to find our first product and most important product for algebraic K-forms, the wedge product of 2 K-forms. Well, you take their tensor product, but that's not alternating anymore, so you take the skew symmetric part of it. And conventionally, you multiply it by that coefficient. What's the point of that coefficient? So that means that if I took, say, 2 linear forms, let's say B1 and B2, which are in Lin 1, the dual space, then by definition, B1 wedge B2 applied to V1, V2 would be, well, the skew part would be B1, V1, B2, V2 minus B1, V2, B2, V1. It would be divided by 1/2, but we define the wedge product without that 1/2. Okay, and if we go down to Rn, where we have a preferred dual basis, then we have a preferred basis for alt Kn, which would just be the wedge products of the dxi's for any choice of k of them in strictly increasing order. And this thing would have the property that if you applied it to E sigma 1 through E sigma k, you got 0, but if you applied to any other increasing sequence, you would get, you get 1, but if you applied to any other increasing sequence of the EI's, you get 0. Okay? So it's pretty simple algebra. A couple of more products. So this product, the interior product, which is also called the contraction, is an operator where you take an alternating k-linear form and a vector, and you product them together. What makes it a product is that it's linear in each of the 2 guys, and you get an alternating k-1 form. And the rule is as simple as it could be. Omega contracted with V applies to k-1 vectors, and it's the same as omega applied to V and those k-1 vectors. Since omega is a k-form, that makes sense. One nice property it has is that if you take the wedge product and you contract it, you'll easily see from the definition that that's the same as contracting with the first one and wedging with eta, and contracting with the second one and wedging with the first one, and adding or subtracting them together. And the coefficient would be, I'll write it one time, but I won't always be writing these coefficients. If we take a J form and a K form and contract with a vector V, that's the contraction of the J form with V, wedge the K form, plus -1. And then you'd use the J form here because you sort of had to move the contraction past J things. And so you get omega wedge eta V. And there are lots of signs like this that arise in this theory, and in the slides I'm always just going to write plus or minus. It never matters, and it's always a pain in the ass to get right. So that's the interior product, pretty simple. There's the inner product, so that's the dot product between 2 K-forms should give you a real number. And we, as usual, we use angular brackets, omega inner product eta. And one way to define it is this. So this requires, so this, I should have said this. This only works if V, oh, I did say it, if V has an inner product, then we define an inner product on alt KV. And what you do is you take any orthonormal basis of V, And then you consider all k increasing sequences of k elements of the orthonormal basis, apply omega to it, apply eta to it, multiply those together, and add it up over all increasing sequences. This you can check quite easily is independent of the choice of orthonormal basis. So this defines an inner product. And the way you should think about it where we use some canonical inner basis, and then what it comes out is that the dual basis that you get from this is then orthonormal. So this definition is cooked up so that these guys will be orthonormal because they're the dual of the EIs, and the EIs are orthonormal in Rn. Okay, so we have a wedge product, an contraction interior product, and there is an inner product on the space of alt k. By the way, people wonder why it's called exterior. It's called exterior, I believe, because you take two k forms and you get something that's not a k form. You get something that's a 2k form. So the product takes you outside of the space. In particular, if you take two 1 forms, they have a wedge product, but it's not another 1 form, it's a 2 form. Okay, now since the dimension of alt kv is n choose k, the dimension of alt nv is 1. And the dimension of alt n plus 1v is 0. There are no alternating forms of higher degree than n. So there's only finitely many of these spaces. But so the dimension of alt nv is 1. That means it's spanned by a single guy. And we can so it's spanned by a single guy. If we were to take one form, so if we fix a particular basis, an orthonormal basis, pick an orthonormal basis of your space, assuming it has an inner product, then we can look around every form in there, except that's a non-zero form, we'll take that basis to some non-zero number, and we can normalize it by saying, well, let's take our orthonormal basis to 1. Well, if we do that, some other orthonormal basis might go to -1. It can only go to 1 or -1. So if we choose one orthonormal basis, which we say should go to 1, that will fix a particular form that's called a volume form. So whenever you have an n-dimensional vector space, take a basis, take another basis. There's a change of basis matrix. And that change of basis matrix is non-singular, so it has a positive determinant or a negative determinant. Okay, so half the bases are related to your original basis by a positive determinant, and the other half by a negative determinant. So you choose one of those two groups and say that's the good group, the plus group. That puts an orientation on the vector space. If you have a vector space with an inner product, then all the orthonormal bases are either the positive ones, the right-handed bases, or the negative ones, the left-handed. And if we pick which ones we consider the positive ones, and we pick our inner product, then there's a unique volume form, and it's determined to be the unique element in alt nv that takes all the positive orthonormal bases to 1. Okay, and then we get this Hodge star operator, which is very important. And here the idea is the following. Take an n minus k form, and take a k form, omega. You can wedge them together, and you get an n form. You get alt n of v. And these are just multiples of the volume form, so you get a certain multiple of the volume form. Okay, so we could think of so this is a certain multiple of the volume form, and so we have wedging with omega. So we have so wedging with omega and sort of dividing by the volume form gives us a map that takes u to, let's call this c omega mu. Okay? Let's actually, maybe I should write it that way, c omega of mu. So pick an omega, and it gives you an operator that, taken any mu, gives you a real number c omega mu, which is the one that omega wedge mu is just that real number times the volume form. So then mu goes to c omega mu is just an operator from alt n minus k to the real numbers. And it's obviously a linear operator, so it must be the inner product with some element of alt n minus k. So this c omega mu must be just the inner product of mu in alt n minus k with something. Okay, that something depends on what omega you started with, so we'll call it star of omega. Okay, and so this is that. So we get that formula that's written right under Hodge star, that omega wedge mu is the inner product of star omega with mu, that's a real number, called the volume form, and that defines an operator star, which takes a k form to an n minus k form. Okay, this is a space of dimension n choose k, and this is also a space of dimension n choose k. And it's easy to see that this is an isomorphism. In fact, if you do it twice, you get it back again, plus or minus. So we have a nice isomorphism from k forms to n minus k forms. It depended on our choice of our inner product and orientation, but otherwise, so it can't be done on any vector space. You need an inner product, but then we have a way to identify k forms and n minus k forms. Okay? Just like we could identify zero form, which is a real number, with an n form, which is a real number times the volume form, once we've chosen what our volume form is. Star star omega is, here I'll write down one more sign. Star star omega is -1, and it's the product of the k and n minus k omega. And again, you always get confused with the signs, but they make no difference, so don't worry about it. What is this on Rn? Well, the volume form is just dx1, dx2 through dxn wedged together. That takes e1 through en to 1. And now it's interesting, this is probably worth your doing, a simple thing to do. Take dx1 wedged through dxn and apply that to v1 through vn, where these are any vectors. Write down the definition of the wedge product, which was skew symmetric part of the tensor product, and you get that this is nothing other than the determinant of v1 through vn of that matrix, which isn't surprising because the only skew symmetric n-linear form on an n-dimensional vector space is the determinant up to a multiple. So the volume form is the determinant in Rn. And the Hodge star says, well, if you give me an increasing sequence dx sigma 1 through dx sigma k, that's a k-length sequence, the Hodge star of it is you take all the other guys, the ones that are in the complement, sigma 1 star through sigma n minus k star, and take that as an increasing sequence with a sign. Okay, so here the star means that sigma 1 through k and sigma 1 star through n minus k star, between them go all the way from 1 to n. Okay, one more operation is the pullback. I could have done this already back at the level of just a multilinear form. So we know if we have v to w, a linear operator, we get an operator back, v star, L star from w star to v star, by the formula L star of some f applied to v is f applied to lv. So you can do that with linear maps, but you can also do it with multilinear maps. So L star of omega applied to W1 through WK is omega applied for LW1 through LWK. And if the omega is alternating, then the L star of omega is alternating. So we get a map from L star, from alt KW back to alt KV. Okay, that's the algebra. Bunch of definitions, none very deep, but they turn out to be very useful. And here is an orange background slide, so the special case of R3. So in R3, well, alt 0 of any vector space is just R. Alt 1 of R3, using the fact that R3 has a preferred basis, that's covectors, that's the dual space of R3, and of course we can identify that with R3 itself. In other words, we could, R3 is things of the form alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. In other words, the vector alpha 1, alpha 2, alpha 3. The dual space is things of the form alpha 1 dx1 plus alpha 2 dx2 plus alpha 3 dx3, and we can identify these. They have the same coefficients. So using our preferred basis, we can identify the dual space of R3 with R3. In other words, I didn't use alpha u. u1 dx1, u2 dx2, u3 dx3 goes to the vector u1, u2, u3. Now, three forms, this is something that's, two forms in R3 are also could be identified with vector fields. And that depends on the fact that it's R3 and not some other Rn. So there's two ways to think about this. They're both worth knowing. One is we could say, what are our basis elements for two forms? Well, there's dx1, dx2, dx1, dx3, and dx2, dx3. It's better maybe to write this as minus dx3, dx1. Wedge product has that switching possibility. And then what we do is we associate this with, there's a 1 and a 2 here, so we associate it with 3. And we associate dx3, dx1, so which is minus dx1, dx3. We associate this with 2, and dx2, dx3 we associate with 1. So that gives you the formula here. u1 dx2, dx3 minus u2 dx1, dx3, or plus u2 dx3, dx1, plus u3 dx1, dx2, we identify with u1, u2, u3. Another way to think about it is a two form is a skew-symmetric matrix. Every skew-symmetric matrix could be written in the form minus u1, or it's actually u1 minus u2, u3, 0, 0, 0, minus u1, u2, minus u3. And we identify that with u1, u2, u3. That's the matrix way to write the operator, which is u1 dx2 dx3 minus u2 dx1 dx3, and so forth. Okay, and three forms can be identified with R because the volume form identifies with 1. So actually, this should say C vol. Oh, it does. Here's C times the volume form. I think I should put these in the opposite order and put the C on the right is an element of R. Okay, those are called vector proxies. Let me say what you could do in n dimensions. In n dimensions, well, you still have alt 0 Rn is R, alt 1 Rn is isomorphic to vectors in Rn. Then it would be alt n minus 1 of Rn is like Rn, and alt n of Rn is like R. But the ones in between 1 and n minus 1 don't have vector proxies. They have sort of skew matrix proxies. Okay, what's the wedge operation? Well, you can wedge together any two forms, but if the sum of the form degrees adds up to more than 3, you get 0. So like that, we don't have to define a 2-form wedge with a 3-form, that's 0. A 0-form wedges with anything, just regular old multiplication by a scalar. A 1-form and a 1-form wedge together, well, that's a vector, and it's supposed to give you a 2-form, which is a vector again. How do you multiply two vectors and get a vector? You take the cross product. A 1-form and a 2-form, that's a vector and a vector, but you're supposed to get a 3-form, which is a scalar. So how do you do that? With the vector proxies, that's just the dot product of the 1-form and the 2-form gives you a scalar 3-form. So the wedge product then is, in different instances, the cross product and the dot product, or the scalar product. What about the pullback? The pullback on 0 forms is nothing. It's just the identity from R to R. The pullback on 1 forms is multiplying by the transpose matrix. The pullback on 2 forms is multiplying by the so-called adjugate matrix. You know, remember the adjugate matrix? It's det L times L inverse transpose. Anybody remember if I should have a transpose here? I think not. No. If it's an invertible matrix, it's that. But this thing doesn't make sense for a non-invertible matrix. But since you have the det multiplying here, the whole thing does make sense. It's the signed cofactor matrix. So just simple linear algebra, maybe if you can't get it, ask me and we can go through this simple calculation. That the pullback gives you the adjugate matrix, and the pullback of a 3 form, that takes a scalar to a scalar, but it's not the identity. It's multiplication by the determinant of L. Let's do that one. So I have a 3 form, which is just some constant times the volume form. And then I want to take L star of omega. So omega of V1, V2, V3 is just C times the determinant of V1, V2, V3. That's the relationship between C and the proxy. This is the volume form. Okay, so L star of omega at V1, V2, V3 is, by definition, omega of L V1, V2, V3. V1, V2, V3. Sorry, no. It's omega of LV1, LV2, LV3, which is, according to this formula, C times the determinant of LV1, LV2, LV3. And you may remember the formula that says that's equal to C times the determinant of L times the determinant of V1, V2, V3. If you don't remember it, think of it geometrically. This is the area of the parallelepiped determined by V1, V2, V3. This is the area of the parallelepiped determined by LV1, V2, V3. And the area gets multiplied by determinant of L. So sure enough, this is that constant times the volume form. And so this constant goes to that constant times dead L. And the adjugate relation and the transpose relation are similar. What's the interior product contraction with a vector space, with a vector field? Well, if you think of a 1 form as a vector, then we need something that takes a vector and gives you a scalar. Of course, it's the dot product with the vector. If you think of a 2 form as a vector, you need something that takes a vector and gives you a vector. It's a cross product with the vector. And if you have a 3 form, we need something that takes a scalar and a vector and gives you a vector. It's the scalar product. What's the inner product on old KR3? If you think of old KR3 as vectors, it's the dot product on those vectors. When it's scalar, it's just the regular product on the scalars. And what's the Hodge star operator? Well, we set this all up so the Hodge star operators are all the identity. So if you think of a 0 form as a real number, and if you think of an n form as a real number, the Hodge star just is it says it's the identity, the same real number, and similarly. So in other words, it says, take your 0 form and think about it like it were a 3 form. They're both real numbers after all. Take your 1 form and think about it as a 2 form. They're both vectors after all. Okay, exterior calculus is now we have a field of these. At every point we have one of these, and we want to differentiate and integrate. So the natural place for exterior calculus is definitely smooth manifolds. And you saw some of the things I did required an inner product on the vector space, and some I didn't. The ones that don't require an inner product are on any smooth manifold, and the ones that do are on a Riemannian manifold, which is a manifold that the tangent space has an inner product at every point. So take a smooth manifold M. So all we have is a bunch, every point has a neighborhood which can be coordinatized, parametrized by Rn. So then at each point x of the manifold, we want to associate an omega sub x, which will be an alternating k-linear form on the tangent space of the manifold at that point. That's the definition of a differential k-form. So if you want to know what a differential form is, at every point x of the manifold, it's an alternating k-linear form on the tangent space. So it takes the point x and k tangent vectors at that point, and it spits out the number, and it's linear in each of the tangent vectors. And then you can say how smooth you want it to be in X. You want it to be continuous or C infinity or whatever the smoothness of the manifold allows you to define. So a zero form is just a function that takes a point to the manifold and gives you a real number. It's just a function on the manifold. A one form is a covector field. At every point, it gives you a covector, and so forth. And so we write lambda k of m typically for smooth guys or unspecified guys, and we write we put a function space in front if we want to specify. So these would be continuous in X differential forms, and we could have C infinity in X or H1 in X if we have a definition of H1 on our manifold and so forth. Special case is where omega is a subset of Rn, and in that case, we have a special basis on old K on the tangent space. So if you have Rn, the tangent space at every point is just Rn itself, or can be identified with Rn itself. So now we're just talking about a map from omega to old KRn, and that's a differential K form. So that's the sense in which a differential K form is just skew symmetric K by n by n by n K times tensor field. That is and we have a basis for old KRn. It's these guys dx sigma 1 through dx sigma k. So that means we can write a general differential K form is just a linear combination of the dx sigma 1 through dx sigma k's where the coefficients are functions of x. Okay, so we can always write a differential K form that way, and there's a lot of engineering textbooks that start the chapter and say a differential K form is something of this form as the definition. But now we've given a definition. It's independent of coordinates, but this is how you would represent it in coordinates. Okay, now suppose we have a manifold M and a manifold M prime and a map between them, a smooth map. So they have to be differentiable manifolds, so we can talk about the derivative of that map. So we have our manifold M here and N here, and we have a point on the manifold with a tangent space. So here's X and the tangent space to X at M. We have a phi that goes here, and of course that creates a linear map from the tangent space from X to phi of X. Also linear maps on the tangent space, M prime. And we can use that linear map to pull back alternating forms at the tangent space to M prime back to alternating forms to the tangent space of M. So here's the formula. If we have a differential form omega on M prime, so that means it takes a point of M prime and tangent vectors at that point and gives you a real number. Well, now we want to define phi star M that should take a point on M and tangent vectors on M and give you a number. So, well, phi star of omega at the point X and the tangent vectors 1 through K, well, you take omega at the point phi of X, and then you push the tangent vectors into the M prime space with phi prime. So those are the formulas. So that's a pullback operation on differential K forms. It's easy to see it satisfies respects the wedge product. The pullback of the wedge product is the wedge product of the pullbacks. And it allows you to find a trace operator if M is just a subset, maybe of lower dimension of M prime. It might be the boundary of M prime or just some embedded submanifold or just a subset, subdomain of M prime. Then we have a trace operator because we have, so here's M prime and here's M in it. And so we have the inclusion operator from M to M prime. And so we can do a pullback under the inclusion of differential forms from M prime to M. And this is so a trace operator. It defines something from the big space to the small space. And if, for example, let's say we're thinking about a one form. So a one form takes a point and a tangent vector at the point at M prime, well, I can think of that point as being in the bigger manifold M prime, and I can think of the tangent vector as being tangent to the bigger tangent space, and then I can forget that my omega acts on all tangent vectors in the big space, and I can only look at it applied to the tangent vector to the small space. So I forget all the other directions, and that's the trace of a one form. No, I'm saying if you have two manifolds with a smooth map between them, then you can pull back. Okay? So if you have, of course, one manifold inside another, the inclusion is a smooth map between those. And so then you can pull back inclusions, and that means you can define traces. So the pullback is defined when the map exists. Just like if you have a L from a vector space to a vector space, if such an L exists, then you have an L star. Okay, and now we really get to some calculus, some derivatives of the differential forms themselves. So the easiest way to define the exterior derivative is use coordinates. There's another way that avoids this, but I won't do it here. So a general differential form is a sum of things of this form, a function times dx sigma 1 through dx sigma k. And the exterior derivative is defined sort of by the formula that you might guess from the notation. So here I'm inconsistent. Here I should have put a sum over sigma because I did a sum over sigma here. So let's say we took the sum here, this one, the sum over sigma, dx sigma 1, dx sigma k. I want to differentiate it. It's a linear operator, so the sum over sigma pulls out. And then I want to differentiate this. Well, these things are constants, so the only differentiation goes on a sigma, and the exterior derivative of a sigma is the sum of a sigma dxk dxk. And that gets wedged with all the other terms, and you do that, and that's the answer. That's the exterior derivative. One thing that comes immediately from this definition is d of something is always 0. And that's worth writing out, and what you'll see is you'll get each of the second partial derivatives twice, but the order of the terms here will be opposite, so they'll cancel each other out. Another thing that comes out immediately from the definition is a Leibniz rule. D of omega wedge mu is d omega wedge mu plus or minus omega wedge d mu, where this plus or minus is -1 to the k if omega is a k form. And another thing that comes out is that the pullback respects exterior differentiation. Phi star d omega is d phi star omega. What if we're on a manifold and not on a piece of Rn? Well, the manifold can be broken into pieces for which there's an isomorphism from phi from a piece of Rn to the manifold. Then we use this formula here. And so we pull back to Rm and then take the exterior derivative there and push forward with the inverse map. So what is the exterior derivative? It's not, so well, let's think about it a little bit on Rn. We start with a function, and then we get a vector field. So it's essentially the gradient. But then we start with a vector field, and we get a skew-symmetric matrix field. So it's not just the Jacobian matrix, which would be a matrix field, but not skew-symmetric. It's the skew-symmetric part of that. And the reason that came up earlier, the reason that's so important is that the skew-symmetric part can be defined on any manifold without a special basis or anything, while the symmetric part cannot. Okay, that's differentiation. There's also integration. And so as I already mentioned, a differential n form on an n-dimensional surface, an n-dimensional manifold, can be integrated. And again, let me give you an idea of what the meaning of it is. And this explains a lot how nice differential forms are in this context. Let's first do a one-dimensional manifold. So what is a one? So we have a manifold, M. And what is a one form? That means at every point x in M, we can take one vector and get a number. So that's in M, and this is in the tangent space to M at x. Okay. Well, imagine, so every manifold can be approximated by a bunch of straight line segments. And these straight line segments, well, these are determined by point, well, let's take one of them here. This is determined by point x here and a little tangent vector v there. So let's call this x sub k and v sub k. So we have x0 and a little tangent vector v0 and so forth. Okay, well, it's quite clear how I should apply omega. So the integral over m, let's call this mh. It's a finite element notation. The integral of omega over mh is just you take omega at x0 and apply it to v0, and omega at x1 and apply it to v1, and so forth. That's sum. Okay? So what did I need? I needed something that takes a vector and gives you a number. That's what a differential form is. Okay? And now we take the limit of this, and that's the definition of the integral of omega over m. And you see why it's really natural that a one form is a covector. It takes a vector and gives a number. I didn't use a dot product to define this, so I don't need to have a metric on my manifold m. If we were on a if we were on a higher dimensional manifold, you'd do the same thing. You take two little vectors and you get a little parallelogram, and you'd build your manifold approximated by a bunch of parallelograms and add up. So there's this incredibly easy definition of the integral, and it's a definition of the integral that doesn't use measure theory, doesn't even use inner products. It's defined on any manifold. The pullback preserves integration as well. Pullback preserves everything. It's really great. So the integral of the pullback is the same as the integral of the guy on the original manifold. Well, you have to worry about changing of sign. If you switch orientation, there'd be a minus sign. And if we go to Rn, then we get, so we have a little piece of Rn, then we can integrate an n form, and an n form is just a multiple a of x times dx1 through dxn. And not surprisingly, the integral of this is exactly what it looks like. It's the integral of that. So if you define this integral through measure theory, you get the same answer. And then, so this is the natural context for Stokes' theorem, in which Stokes' theorem becomes a pretty easy theorem. And so the integral of the exterior, so now we take a k minus 1 form. If you take the exterior derivative, it's a k form. If omega is a k-dimensional manifold, you can integrate it. On the other hand, the trace on the boundary, the pullback of the inclusion, will make this a k minus 1 form on the boundary. Boundary omega is a k minus 1 dimensional manifold, so you can integrate that, and those are equal. That's Stokes' theorem. And that includes, as special cases, the fundamental theorem of calculus, the divergence theorem, Green's theorem, Stokes' theorem, as we learned it in calculus. Okay, once you know Stokes' theorem, you can combine it with the Leibniz rule, which was d omega wedge eta. So if I take the integral of d omega wedge eta, that'll give me the integral of the trace of omega wedge eta. And traces are pullback, so they preserve wedge products, so that's the integral of the trace omega wedge trace eta. But d omega wedge eta is d omega wedge eta plus or minus omega wedge d eta, so we get this integration by parts formula directly from Stokes' theorem. If omega is a k form and eta is an n minus k minus 1 form, d omega wedge eta is an n form, we can integrate it. Omega wedge d eta is an n form, we can integrate it, and you get the same answer plus a boundary term, which is the integral of wedge products of the traces, which is an n minus 1 form, so we can integrate it on the boundary. Now that's all works on any manifold. If we have a metric on our manifold, so it's a Riemannian manifold, then I can introduce an inner product, and instead of talking about wedges, I can talk about inner products with Hodge stars. And so, okay, and here was the formula. You just apply, okay, there's a little bit more to say here. If you have an oriented Riemannian manifold, then in every tangent space, we have the Hodge star on all k tangent spaces. And an oriented Riemannian manifold does have a measure on it because it has a metric on it, and so you can say that an orthonormal basis has measure 1, volume 1. And so we can talk about taking the inner product at every point and then integrating it over the manifold, so we have an L2 lambda k inner product on a manifold with a metric, a Riemannian manifold. There's the real formula. At each point you take the inner product as algebraic k forms, that gives you a real number, and multiply that times the volume form so you can integrate it. And because the way we define the Hodge star, we know that this inner product of omega and eta is the same as the wedge product times vol is the same as the wedge product of omega and star eta. So these are equal. So this is another way to write the L2 inner product. Now, if we plug that into here, so we replace all these things with inner products with the Hodge star, and if we define an operator in the following way, take a k form, star it to make it an n minus k form, differentiate it to make it an n minus k plus 1 form, and star it to make it a k minus 1 form with the right sign, call that delta u. So let's just do that picture. So I have a 0 forms, 1 forms. Let's just do it through 1 forms, n minus 1 forms, n forms. So I can take the Hodge star and identify these two spaces. Then I can take D and get over to here. Then I can take the Hodge star back again and identify these two spaces. And so altogether I've got a mapping from here to here, which is really just this mapping, but instead of thinking it from n minus 1 to n forms, we think of it from 1 forms to 0 forms. What it would be if we were talking about C infinity functions in R3 to C infinity vector fields in R3 to C infinity vector fields in R3 to C infinity functions. And this is grad div curl div. Then this is D, D and D. This delta that goes this way would be take this vector field, think about it as in this vector field, take its divergence, and think of that scalar as this scalar, so this would be div. So it's the formal adjoint of gradient. I didn't say anything about boundary conditions or anything. So delta is just the formal adjoint of D. So if you use that definition and the Hodge star, you get a different way to write this integration by parts, but it's the same information written in a different way. The L2 inner product of d omega and mu is the same as the L2 inner product of omega and delta mu, the co-derivative, formal adjoint, plus a boundary term, which is the trace of omega wedged the trace of the Hodge star of mu on the boundary. And omega is a k minus 1 form, and mu is a k form. So star mu is an n minus k form. So we have an n minus k and a k minus 1 form. So this is an n minus 1 form. So it makes sense to integrate it. Actually, this business that you count things and see whether they make sense or not is a great help because it really helps you from making mistakes. You couldn't have put a star on both things. It doesn't make any sense. Okay, and now let's look at the calculus using vector proxies in Rn. So we have vector proxies for 0 forms, 1 forms, n minus 1 forms, and n forms. So 0 forms, the algebraic guys are real numbers, vectors, vectors, numbers. So the differential guys are functions, vector fields, functions. On the boundary, 0 forms are functions. 1 forms are vector fields on the boundary, so tangential vector fields to the boundary. Now n minus 1 forms on an n-dimensional space, that's functions again. And n forms on an n-dimensional space is 0. N forms on an n minus 1-dimensional space is 0. The trace operator takes a function to its restriction on the boundary, which is a function. It takes a vector field, and it has to give us a tangential vector field. It's the tangential projection, the orthogonal projection in the tangent direction, and onto the tangent plane to the boundary. An n minus 1 form is another vector field, but now the trace operator has to give us a function. It's just the normal component, u dot n. So the traces capture those operators all in one definition of the trace. The D operators are, of course, grad curl, and where this curl has to be understood in n dimensions as taking a vector field to a skew matrix field, which would be the next thing. In 3 dimensions is a vector field to a vector field. And then when you get out to n minus 1, this takes vector fields to scalar fields. That's the divergence. And the other ones that are in between don't have names. They're just D. And now the delta is the formal adjoint of the previous D. So for 0 forms, delta is 0 because it maps to minus 1 forms. For 1 forms, delta is negative div. For n minus 1 forms, it's the curl. And for n forms, it's minus gradient. Okay, and the integral of a k form over a k-dimensional space being a real number, well, if we have a 0 form, we have to integrate it over a point. We just evaluate the function at the point. Counting measure integral. If we have a 1 form that's a vector field, we have to integrate it over a curve. It's just the integral of the tangent. It's the line integral of u dot t with the one-dimensional Hausdorff measure over that curve. The n minus 1 form is a vector field, and we have to integrate it over an n minus 1 dimensional surface. We take its normal component, that's a real number, and integrate it with the n minus 1 dimensional measure. And the integral over the full n-dimensional manifold, n-dimensional domain of a function is just the usual Lebesgue integral, n-dimensional integral of the function. And finally, the pullback. Well, we figured out the pullback in the algebraic case. It didn't do anything to u for 0 forms, but of course it moves it to a different manifold, so it's u composed with the map. So the pullback is just composed with the map. The pullback for 1 forms is composed with the map and multiplied by the derivative transpose. Remember, we had an L transpose for 1 forms. For n minus 1 forms, it's composed with the vector field with the map and multiplied by the adjugate matrix. That's the thing that's known as the Piola transform. So I always regard it as mysterious when you deal with elasticity and stuff, or you deal even with divergence operators. You always have to use the Piola transform. That's because that's the pullback for n minus 1 forms. And the pullback for n forms is multiplication by the determinant, a change of measure as well as that. So again, the nice thing is all these operations are defined once and for all, most of them on any manifold or a few of them on any Riemannian manifold. What else do I have here? Okay, now we go to the Hilbert space theory. Let's take a domain, assume it has a half-decent boundary. So now we're going to need some properties, a Lipschitz boundary. Then, of course, Rn has a metric, so we can define the L2. L2 lambda k just means differential forms, and then you take their norm at every point and take the integral of it squared. And then we could ask whether du is also an L2. This is the thing we defined previously. So we have a closed unbounded operator D, and this is the graph norm and so forth. This is its domain. So we have H lambda k is L2 k forms. This is with the space I did is called V when we were doing abstract Hilbert complexes. And H star lambda k is defined, well, you have to be now here you have to be careful. This is things in L2 whose formal adjoint or co-derivative is in L2. I didn't put any boundary conditions on it. So this space is not the domain of D star. This space is just things that sort of formally, if I didn't think of boundary conditions. So this would be vector fields whose divergence is in L2, and the other one is vector fields whose curl is in L2. But we know for those to be dual to each other, one of them should have had a boundary condition. And the Hodge star is so defined, and the delta is so defined, that H star lambda k is the Hodge star of H star lambda n minus k. So the way I think about this is H star 1 is H div if you think of it sitting in the 1 form space. If you think of it sitting where H curl ought to be sitting and put H div there. Okay? Now we have a slight bit of analysis. You can prove that a function in h lambda k has a trace which is in the space h minus a half lambda k. So in other words, you define the Sobolev space h plus a half lambda k on the boundary, which just means differential forms whose coefficients are in h plus a half, and it's possible to make sense out of this integral. That requires a Lipschitz boundary, because even to have a trace of a h1 function, you need to have a nice boundary. Of course, similarly, absolutely analogously, if you have something in h star lambda k, then star u has a trace in h minus a half of lambda n minus k. And therefore, we can define h0 lambda k and h0 star lambda k as the things with traces equal to 0. And then we get to the unbounded operator context. If we think of D as an unbounded operator from L2k forms to L2k plus 1 forms, and we take its domain to be h lambda k, then D star is delta, but not with the domain h star lambda k, with the domain h0 star lambda k. Okay, so this is a calculation from these definitions. And therefore, harmonic forms in this thing, that's things for which D is 0 and D star is 0. So those are things in L2 lambda k such that D is 0, delta is 0, and the trace of star omega is 0. So it's an H0 star lambda k. So everything I wrote there is sort of easy formal stuff, except the stuff involving trace, where we had to take into account we had a Lipschitz boundary. And I'm not going to prove that, but I want to explain one thing that might puzzle you. You're used to the fact that h1 omega has a trace, and it's in what space? h1 half, not h minus a half, h plus 1 half of boundary omega. And in fact, it's onto that space. You can deduce that from what's written on the board, even though we have a minus 1 half. And why is that? Because if u is in h1 omega, then according to that board, trace u is in h minus a half, so this is really h1, h lambda 0. Then trace u is in h minus a half lambda 0, which is h minus a half of the boundary. However, d of trace u, so trace u lives on the boundary, so that's the d on the boundary. This is a 0 form on the boundary. Well, what? Yes, I could. Oh, thank you. D on the boundary applied to trace u. Well, this is a 0 form on the boundary. So this is the gradient on the boundary. But trace is the pullback of inclusion. And pullbacks commute with exterior differentiation. So this is the same as the trace on the boundary of D in the whole domain of u. Okay? And D of u is in h lambda 1, because D takes h lambda 0 to h lambda 1. So the trace of D of u is in h minus a half 1 forms on the boundary. So actually, this would have worked not only for 1 forms, for k forms. What we just proved is that the trace on the boundary of u is in the set of u in h minus a half lambda k. If u is in h lambda k of omega, then the trace of u is in the set of things in h minus a half lambda k of the boundary omega, such that d, sorry, I shouldn't call this u, say v, such that d on the boundary of v is in h minus a half lambda k plus 1 of boundary omega. So the trace operator is into a special subspace of h minus a half, those things in h minus a half for which d stays in h minus a half. So now when I go up to 0 forms, we're talking about that the trace of u is in h minus a half, and its gradient is in h minus a half. So trace u is in h minus a half of boundary omega, and the boundary gradient of trace u is in h minus a half on boundary omega. Well, of course, the gradient is all partial derivatives, so these two things together says that the trace u is actually in h plus 1/2 lambda 1. So what if we applied the same kind of reasoning to an h curl function? What is the trace of an h curl function on the boundary? So if u is an h curl, well, that's h lambda 1 of omega, let's say 3D. Doesn't really matter if it's 3D or not. Then we have the trace in the sense of h1 forms, which is the tangential, so trace u is really u cross n. This is in h minus a half of boundary omega, but it's a special function in h minus a half. It has a property that d of it is also in h minus a half. This is a 1 form, by the way. And by d of it, we mean d on a 1 form. So that would be on the boundary, which is a 2-dimensional thing. That would be the road operator. So u cross n is in the set of v in h minus a half, such that road on the boundary of v is also in h minus a half. And that space is not the same as h plus a half. And what do you get for div? In that case, let's see if we can do it in our head, the trace of something in h div will be in h minus a half. And then now you'd put the d on the boundary, but that would go to 0 because there's one level down and we were already at the last level. So the trace of an h div function is h minus a half and no better. Okay, so the answer is, in general, the trace of a h lambda k function is an h minus a half function for which d of it on the boundary is also an h minus a half. And for 1 forms, that gets you up to h a half. For n minus 1 forms, it just leaves you down in h minus a half, and in between it's something in between. What's that? This is the 2D, so when we write down the 2D sequence, we have h1, gradient gets us to vector fields, which I call h-rote, and this is the scalar curl that takes a vector field to a scalar field, right? So it's the one that takes u1, u2 to minus d1, u2 plus d2, u1. That's rote.
Your omega is in R3, right? So your boundary is also in
No, so this u is a vector field in R3. So u cross n is a tangential vector field on the tangent space in R2. Right? U cross n is in the tangent space. It's a 2-dimensional vector field. So you can take a 2-dimensional root of it and get a scalar field. If you have any 2-dimensional plane and you have a vector field in that plane, you can take rote and you get a scalar field. Rote takes 2 vectors to scalars. Yes? So we start out with u is a 3-vector. U cross n is a tangential 2-vector to the tangent space. Okay, since I have a vector in a 2-dimensional space, I can take rote in that 2-dimensional space, and I get a scalar on the boundary. U cross n is the tangential vector field. Yeah. Okay, 2 more. Hold on 1 second. So I have 2 more slides, and I'm already 5 minutes over. Can I still let Jin Chao talk?
No.
Oh, well, then I'll let him talk. It's up to me. I'll let him talk.
I'll ask you later.
Okay. So let me just finish up. So now what I'm doing is I'm saying, okay, we define differential forms. It went by awfully fast if you never saw it before, but it's not terribly deep anyway. And now we want to use those spaces to define the de Rham complex that is a Hilbert complex and stuff. So I have to think of how D is really can be thought of as an unbounded operator, and I did that here. Here's how we take the domain. Then I have to figure out what its adjoint is. So then we said what its adjoint is. And so now we have a de Rham complex on a domain in Rn, which is you take zero forms, which are in L2, and their D is in L2, and you take D of them. So their one form's in L2, and their D is 0, so they're in H lambda 1. You take D of them, and so forth. And then we have a dual complex back, and that would be with the deltas, except all the spaces would be the star spaces with boundary conditions. We get the dual complex. And now there's the second place where you have to actually do some analysis. And this goes back to R. Picard in 1984. He took a Riemannian manifold with boundary, but we can think of a domain in Rn with Lipschitz boundary. And he said that the compactness property holds, which means that the intersection of one of these spaces with the corresponding one below is compact in L2. Okay, that's true for any domain with Lipschitz boundary. The name of the paper is an elementary proof that, so it's not too hard, but it's not that easy either. And then I remind you that the compactness property implies Fredholm. That's because the compactness property implies that the harmonic forms are compact in themselves. The inclusion of the harmonic forms is a compact operator, and that means the harmonic forms have to be finite dimensional. So it's Fredholm, and a Fredholm operator is always closed. So now we have good news. This de Rham complex is a closed Hilbert complex. And the closed Hilbert complex is what we now know everything about. And so tomorrow, we'll start building the differential, the finite element forms that'll give us subspaces with bounded cochain projections. Thank you.